In this video, I want to look at a problem where there isn't constant acceleration throughout, but you can break it up into parts where there is constant acceleration in each part. The problem is with a toy rocket that goes straight up with a constant acceleration of 4.5 meters per second squared. After 100 meters, it releases a small metal ball which falls to the ground. Since the time the rocket launched, how long was the ball in the air? And we'll ignore air resistance again. The first thing is always a picture. I have a blue rocket. It starts at the ground. It goes up 100 meters, at which point a small ball is released. I've represented in orange. The ball will go up a little further before it falls back down. If that isn't clear, remember, the ball is moving with the same velocity as the rocket, and so when it's released, it has some upward velocity. I need a coordinate system for this, with a 0 in a positive direction. I chose the 0 to be at the ground, the place where the rocket started, and I chose positive to be up. What to do next? The first thing I did is I drew a graph. I want to know about the acceleration, and so I drew an acceleration graph as a function of time. I noticed that it's constant initially and positive, given my coordinate system, up to some time t. So I've identified this time, which I've called small t, to be the time at which the ball is released. At this point it's in free fall, and I know that its acceleration in free fall is negative 9.8 meters per second squared. So here I have two regions in time. The acceleration isn't constant throughout the whole problem, but it's constant in these two regions. So if I break these two regions into region 1 and 2, I can use my constant acceleration relationships in those two regions of time. So let's look at region 1 first. I've recreated my picture. My first step is to identify specifically 2 points in time. The initial time is the point where it's launched, and I'll set that to be equal to time is equal to 0. And the final time for region 1 is the time at which the ball was released. So the region of time is this whole blue region where the rocket goes up right to the point of the release of the ball. And I called that time, that point of release, just to be small t. Now I want to list everything else I might know between those 2 points in time. The first thing I can calculate is the time difference, which in this case is again that small t, representing the time of release. The initial position, given my coordinate system, is also 0. The final position I know, it's at the point of release, and given my coordinate system and the information from the problem, that's 100 meters. The initial velocity, well, that's when it was launched, that's 0. The final velocity at this point of release is something I don't know yet, so I just called that v, the acceleration I was given, which is 4.5 meters per second squared. Now, I know a lot of people will keep their units through here. There's meters and meters per second squared. Quite frankly, I go back and forth on that. It can also complicate the math quite a bit, and I'm not sure the extra complication is worth it. As long as I know at the beginning I'm in SI units, then I know that the SI units continue throughout. So now I have what I know and I don't know, and I have a set of relationships between those parameters, and I want to use them now. There's a fourth equation that I never use, almost never use, and so I've kept these three. This one I use in most cases where I don't know or don't need to know time, and since time is a huge part of this problem, I'm going to start with the first two. If I look at the first one, I don't know v final, I do know the initial velocity, I know the acceleration, and I don't know the time difference. So there are two unknowns there. I can put into that relationship what I do know. So the final velocity I've just represented as v here, and that's equal to the initial velocity, which is 0, plus the acceleration times time. Note I did not put in 4.5 for the acceleration because I like to keep things in terms of the parameters and only plug in numbers at the end. That way I can maintain the relationship between physical quantities. Note that here there's a big exception to that rule. If there are zeros, I put those in as soon as possible because that's going to simplify the math quite a bit. So there's still two unknowns to that one, so let's look at the next equation. The final position I know, the initial position and velocity I know. I know the acceleration. In fact, I know everything in that relationship except the time interval delta t. So I can just use that equation to solve for delta t exactly. And so I'm going to do that now. So here's this intermediate range between brainstorming and solving. I'm still brainstorming, I'm accumulating information, but here's a point where I can see, hey, I can solve for new information. I'm going to do that now before I go on. Putting in my numbers, final position is 100, initial position is 0, initial velocity is 0, then 1/2 a time interval squared delta t, but delta t is just t. And now I can solve for t by multiplying both sides by 2 and dividing by 4.5, and then taking the square root of both sides to get 6.66 repeating. When I saw that number, 6 repeating, that immediately drew a red flag for me. I looked at that and said, that is a ratio of rational numbers. I mean, 6 repeating, what is that? That's 2/3, right? So that's 6 2/3. That 6 is 18/3, that's a 20/3. When was the last time you took a square root of something and got a rational number? So I went back just to check to make sure I didn't have a calculator error. If I put in 4.5, what is that? Well, that's 9/2, right? 200 times 2, well, that's 400. 400 ninths? Yep, that's exactly right. Square root of 400 is 20, and the square root of 9 is 3. And I like keeping it in terms of 20/3. That may simplify my math later on, but my main reason is just to make sure I calculated it correctly. Now that I know the time, I can go ahead and calculate the velocity. I had that up here. Again, I'm just sort of accumulating information at this stage, and there's no reason I can't go ahead and calculate something once I know how. Again, I'm going to keep things in terms of whole numbers because that allows me to avoid calculator error and it makes the math easier. The acceleration is 9/2 times the time, which is 20/3. I cancel 9/3 is 3, 20/2 is 10, 30 meters per second. And that's another nice thing doing this. I don't have any rounding error either because I'm keeping everything in terms of integers, and you could even use your calculator to check to make sure you did the arithmetic correctly. I now know everything in the first stage. There are no longer any unknowns. However, it doesn't get me what I want, which is the final time. And I knew that I'm going to have to look at the second stage now. Now I want to look at stage 2, which represents the orange part of the trajectory. Of course, it's one dimension. It goes right up and back on itself. I sort of drew it off so it was clear to me what was happening. But it goes straight up for a while, and then it comes right back down to the ground. What are my 2 points in time? For this stage, it's the point of release and the time it hits the ground. So what are those? The initial time in this stage is the final time from before, which I found to be 20/3 seconds. The final time is now the total time of the entire problem, and that's in fact what I'm looking for. So once I get that, I'm done. What's the initial position? The initial position is at the point of release for this stage, which is at 100 meters. And what's the final position? Well, when it's back down to the ground, which is 0. What's the initial velocity? Well, it's the final velocity from the last stage, which we found to be 30 meters per second. And what's the final velocity? Well, it's unknown, so I just represented that as v sub f again. Now, I know a lot of students at this point who would want to put in 0 here, because they say, well, the final velocity when it hits the ground, and when it hits the ground, it's at rest. You can't ever do that. And the reason is, once it starts to hit the ground, of course, its acceleration now is completely different. It's coming to rest in a few milliseconds. And so you can't use constant acceleration relationships that cover free fall and the really high acceleration when it's stopping when it hits the ground. So whenever we say when it hits the ground, we're talking about that instant right before it hits the ground. And in this entire region has to have the same acceleration. And that acceleration is negative 9.8 meters per second squared. Negative, of course, because of our choice of coordinate system, which was positive up. We can go ahead and calculate the time difference, or identify the time difference, which is usually important, which in this case is the total time minus 20/3. Now we have relationships between all these parameters, which I've brought back. Well, I don't know v final, and I'm trying to find the time interval. So maybe I don't want to start there. This one worked well for me before. The final position I know 0, I know the initial position, I know the initial velocity, I know a. Look, again, this second equation, I know everything except the time interval, so I can go ahead and solve for the time interval immediately. If I go ahead and start plugging in the numbers into that, the final position is 0, initial position 100, 30 for the initial velocity, and negative 9.8 over 2 is negative 4.9. I've just recast that. It's a quadratic equation. In our traditional quadratic equation 4, ax plus bx plus c is equal to 0, and I can look up the solution for quadratic equation, which is negative b plus or minus b squared minus 4ac divided by 2a. My calculator for the term in the square root was 53.479, and so now I'm going to get two solutions for this. The negative solution, which is negative 2.61, and the positive 8.52. This will happen where your math gives you multiple solutions, but only one is correct. Of course, we're doing physics and not math, and so you have to go back to the physical problem to see which one is correct. And of course, the time difference is going to be positive because the final time is later than the initial time, so we can rule out this answer, and the answer is positive 8.52. The time interval, which is the total time minus 20/3, gives us the total time is then the time interval of the second stage, remember that's what we found, plus 20/3, and we can now find the final time with 15.2 seconds. Our final step is to check. We don't have a lot of relationships to check. Mostly it's a matter of does this make sense? And it's not milliseconds, it's not years. 15 seconds seems like a reasonable amount, so we'll have to be confident with that.